Yeah, welcome back. Now for part 2. Again, small outline. This is a bit less. I don't actually think I'll end up at the whole 1.5 hours, but I wanted to have some time for more questions and answers, hoping that this time there actually are any. Yeah. The first one, which is called Dictionary Schemes and Context Models, if that doesn't mean anything to you, we'll see it later one. A bit of theory still. I'll try to keep this short because it's not really that important that you understand the details. And then we'll get into this section, which is just 2 subtopics, but both are, I'll talk about both extensively because this is how to reorder data and how to make it compress better. And this is, I think, what most of you are interested in. And I'll need the background from the section 4 for that. Okay, so on to section 4. And more specifically, so-called dictionary methods. In most types of data, you have lots of repetitions, which are usually a really high count of small 2 or 3 byte sequences that get repeated. But there are also a few really, really long ones, like when you would copy a whole subroutine from your program somewhere else, you would get a very long sequence that's exactly the same, stuff like that. And how can we make use of that to make it compress better is the main question. And the idea is that you don't code each character individually, like you would in our previous section, but instead try to code whole strings with a dictionary, which is not the normal hardcover kind. You don't have a book of English words used for that, but rather you build a dictionary from the data you've seen so far, from the compressed data. That's the idea, because again, this ensures that your dictionary actually matches the data. If not the current data, at least the past data. And if the current input is found in the dictionary, like the 5 characters that are coming up right now, for example, you don't store those 5 characters individually, but a reference to the dictionary where those 5 characters are. And this reference is usually smaller than the string itself, because that's the whole point. You try to make those references small, so this kind of encoding pays off. Yeah, there can be either explicit or implicit dictionaries. An explicit dictionary is an algorithm that really has a dictionary, a table of strings, and maintains this explicitly. An implicit algorithm is anything that doesn't do this and generates this from the data somehow. The dictionary is not stored along with the data. This is not something you put in the header or similarly, like you would, for example, with vector quantization. Not a table you store anywhere, but a set. It's being built from the data. And this is not something you do in a pre-processing step, but this happens as you are compressing it. And it's built on the fly. Explicit dictionary methods are basically quite dead, because implicit coding is easier to combine with other algorithms for various reasons. And all good compression methods that you will see nowadays don't have a single algorithm they use, but try to combine different techniques, because each technique has its strengths and weaknesses, and when you combine several of them, you are usually able to get a good mix that allows you to get really, really good compression for a wide range of data types. But for completeness on explicit dictionary methods, for example, LZW, Lample-Zip-Welch, is an explicit dictionary scheme, which is used in, for example, Unix compress tool, which no one uses anymore, the CompuServe GIF file format, and the modem V34 protocol, and so on. This used to be patented, which was a lot of trouble in the last few years with, for example, GIF files you had on web pages. The patent is now expired, but this patent basically nails shut the coffin of explicit dictionary schemes, because they didn't have the pack rate you would get with other techniques, and now with the patent trouble, no one used them anymore, so they're basically, not popular anymore. So, implicit dictionary methods. The most popular, most well-known of that is the so-called LZ77 scheme, variants of it, which is done by Abraham Lempel and Jakob Ziff in 1977. This is really probably one of the most important publications in the data compression world, because this algorithm is the basis for, basically most packets you've used in your life. There are things like APAC, which is a DOS4K packer, or also bigger files for the packer used in UPX, or combined with Huffman coding, you get basically all popular packers like LHA, which is again pretty much outdated, in ARJ, but also zip, RAR, CAP, and so on. Or if you combine it with arithmetic coding, you get LZMA, which is used in 7-zip and several current executable compressors, or Crunchy, which is a different variant of coding but also uses LZ77 combined with arithmetic coding, and lots more. This is really, really popular, and everyone of you in this room probably has used a variant of this in some way or other. What it does, it uses a so-called sliding window of fixed size. For example, in zip files, this is the last 32 kilobytes that you have coded. So it tries to predict whatever is going to come up from the last 32 kilobytes it has seen, and tries to find matches with those 32 kilobytes. And obviously, longer matches are better. If you find a match, several characters that match, for example, 2,000 of them, 2 kilobytes, you obviously can get a really, really big compression from that. But if the longest match you can find is something like 3 characters, depending on where in the window it is, it might be beneficial not to code it at all. So the longest match is not necessarily the best one. If you don't find any match with this history window with the last 32 kilobytes at all, then you just try to code it as is with whatever you used before. The result is a sequence of tokens, or so-called literals, which is just data that is stored literally, that is not changed in any way, and so-called match tokens, which are a reference to data that happened, say, 2 kilobytes before, 4 kilobytes before, whatever. And this compares to packet-based RLE schemes I mentioned earlier, because you have those packets of data that mark repetitions, and it's coded in a very similar way. Then you try to encode this token sequence. In plain LZ77, this is a fixed size code with a few bit fields that's used to code everything. Then there were further variants like LZSS, which has first a bit that tells, is this a match? So we have a reference and an offset in length here, or is this a plain character, in which case we just store the character. Or zip, which does some Huffman coding on top, and newer algorithms do arithmetic coding and even fancier methods and try to predict things, but it's basically always the same general idea with some processing afterwards. The take-home lesson on this, if you use something LZ-based, and you will, if you use an executable packer, you probably will have a packer that is based on the scheme, you wanted to find long matches. So you want long string repetitions as is, that really just one string that appears multiple times. And if you manage to make data repetitive, so you have lots of repetitions, it's a good idea. And that's one of the reasons this kind of reordering is useful. Because if you have data that would match, say, every second character, you don't get any string matches at all. Because, it's just every second character, nothing continuous. So if you manage to make it be every character that matches in one part of the data and no matches at all in the second part, then you have a compression gain. And this is the main reason why you would do reordering on data. And the other part of this section is so-called context modeling techniques, which is a class of modeling techniques for arithmetic coding. As I told you at the end of part 1, in arithmetic coding, you don't need actual value counts. You just need probabilities. How likely is the next character going to be an A and B, whatever. And what you do is you predict the next symbol based on context. When context in this case means the last few characters you've read and the last few characters you have encoded, like last 2 or last 3. And then you collect statistics. how likely each character is going to happen in that context, and then build an overall prediction from that somehow. You usually have several contexts of several lengths and so on for a single character, and you have to mix that to get a good estimate of what character is likely to appear next. This somehow, how this is mixed and how this is calculated, is the main difference between algorithms, plus the details of how statistics are collected, because everyone has different data structures for that and so on. Some are more efficient, and some give better results than others, but yeah, it's really just a variation on the same theme. This type of coding has produced some of the best compressors you will see in the real world. I think by now the best general purpose data compression algorithm is PAC 7 or PAC 8, which is an algorithm that is based on this idea. But the drawback is you do a lot of work to predict individual characters. You have to look at different contexts, you have to calculate how probable each character is, you have to do arithmetic coding, so this is really, really slow. For example, a PAC, like I just mentioned, is very good compression-wise, but it also compresses like about 9 kilobytes per second on a state-of-the-art machine, and it uses a few hundred megabytes of memory for that. So that's obviously a high price you have to pay there. So you can get very fancy with that, but it's not for free. And so the modeling details of how you would do that are rather technical, and it's not really interesting in the seminar. And as a user, I would recommend you treat it just like it is LZ with arithmetic coding, because it really benefits from the same kinds of things, like characters, long matches and stuff. This gives good compression in this kind of schemes too. And I only mention this because some next generation exapackers like Crinkler or a new experimental version of Crunchy I'm working on right now are based on ideas like this. So it may become important in the next few months or years. Which brings us to section 5, which is, basically most hands-on of all of those sections. And the first, it's about how to reorder data so you get good compression. The first one is about operator systems, so like our Farbrausch tools, where you have stacked operators. And the second one is about how I record a code to make it pack better, which is probably not of much interest to you as it is, but it shows some of the nicer things you can do in this reordering context. Okay, so on the operator graph tool, you've probably seen this kind of data structure, this kind of way of thinking, if you ever used a Farbrausch demo tool, or at least seen screenshots. And we have those blocks which are connected, in our case by stacking, or some use arrows like in Buzz. Data is moved from one point to the other and that kind of thing. And other tools that are not this explicit about the way they do it still use a similar representation of operations arranged in a tree internally, even though the user doesn't really see it. So this is probably the way most intro tools work internally. And successive operations on the data you do are stored together with the parameters. This by itself is nothing spectacular. Every application that has any kind of undo functionality has to do that too. So it can revert operation, it needs to know what exactly has been done and have a reverse step. But in our case, and that's the interesting part, the history is not a linear list of operations, but a tree. So you can make branches. You can use the same source for two different destinations. You can have links between the things. And this is really a lot more flexible. And more precisely, it's not really a tree, but a so-called DAG, a directed acyclic graph, which basically looks like a tree, but also allows you to have a limited way of relationships that are not really tree-like. So you can have pointers upwards too. This operation history of what has to be done to reproduce the intro data that the graphician did is then stored in the intro. So we're interested in how to make that pack well, because that is the main part of data we would store in any intro. And well, first, this is basically a tree, or looks like a tree at least. So you can do standard techniques you would do in trees. When you have a tree, you can do something called post-order traversal, which basically means you just recurse down into the tree, and by the point you're out of recursion and you're returning back, you write which node you're currently on. For example, this is a color correction operation. And when you know how many inputs each operation gets, that's all you need to know. You just need this operation, and by the way things are stored, you automatically generate everything in the right direction. So you do this post-order traversal and write out operator type IDs that just tell you what kind of operation is happening now, color correction or generate a cube, that kind of thing. And you write it out as you go, and that, together with the parameters for the operation, is all the representation you need. It's said it's not technically a tree, but a DAG, so you can have this kind of back pointer stuff, and children that have several parents, so to say. So you have things that couldn't happen in a real tree, and you have to use some escape codes for the exceptions, for stuff that couldn't happen in a tree. You need a special symbol for that. You basically just pretend it's a tree and code exceptions when it's not. That's the most efficient way to store the structure of this operator graph, of the data flow in the intro. But it's not the most efficient way to store the parameters to these operations. Because don't understand the concept.
How do you know this way is most efficient?
Because it's very implicit. You this kind of stuff you need to code. Yeah, you code a minimal amount of information. You need the minimal amount of information. Yeah, well, it's a minimal amount of information you need to code. You need those operator type IDs anyway. And any other way to code it needs some additional information as well. I mean, this is not mathematical.
Well, that's a proof. That's a proven fact. That has been proven 30 years ago. I mean, that's just basic knowledge. You can prove that the entropy is exactly that, the post-traversal ordering.
But this is DH done. This is DH key.
Yeah.
So this exception, escape code. Okay.
Yeah, sure. This is not.
I don't know if it's most efficient.
I don't mean it in a way, as in you couldn't squeeze a few % out of that, but you could probably do some fancy escape coding stuff, but it's not really relevant to what I'm trying to say here, so I just skip that. And yeah, of course it's a risky statement, and you could probably prove me wrong, but I don't think it's really relevant at this point. So I'll just skip this discussion and go on with the operator parameters. Because the problem there is that those parameters are different beasts from the type IDs. They have a different structure. The straightforward way is to store that together with the op type. So you just store this op type, and then the parameters for this op, and the next op in this post-order traversal. When you do that on the data set we use in the Krieger beta version, you get about 30 kilobytes packed again with a simple encoding I mentioned. But a fact is that, again, operators of the same type, like most cubes, have a very similar setup, because certain parameters like tessellation you usually don't change. You want those in any way, because some cubes need a special tessellation, but a lot of cubes will simply be 1 by 1 by 1 faces, and that kind of stuff. So operators of the same type tend to have similar data. And this tells us that it's a good idea, probably, to try to group them so we can exploit the differences between them better. And so what we try is we store all operators of the same type together. But to do that, we obviously need to store the tree and the operator parameters differently in a separate way, because by now the operator data doesn't happen in the same way, in the same order as it does in the tree. When you do that, you get about 28 kilobytes, or about a 7% gain in compression ratio. And the changes to the loading code are really quite minimal, because it's undoing this reordering is basically just changing, just building a list of pointers first where every data is, but and you have to assert it first, but it's not a big problem. It's not a lot of code, maybe 50 bytes additional. So this is no huge gain in compression you get there, about 2,000 bytes, but it's at a cost of about 50 bytes of code. So it's an easy saving. It's really a no-brainer to implement, and this kind of stuff, if you do several things like this, it can give you a nice gain in compression without having to do a lot of work. And the second example I was going to mention is x86 Intel architecture code. Basically your intro is probably at least half of it is code. The source code is usually in a highly structured form. You use structured programming languages which have for loops and while loops and the like. So you try to make it's a relatively high level representation with a lot of explicit information. And if you look at the compiled code, it looks quite unstructured. It's basically a sequence of just straight line code with some if and go to instructions. That's what it maps to on an assembly level. And when you view it in a hex editor, you get a sequence of very random looking bytes. So there are two possible explanations for this. The first one is that this process of compiling source code into executable code completely destroys the structure that was inherent in the source code, be it relatively low-level stuff like the basic program flow, or relatively high-level stuff like control structures. The other explanation would be that this encoding of instruction still has that information somewhere but hides it. Both of those are true in part. Use some of the structure because as said, what a compiler basically does, it converts all kinds of loops into ifs and go-tos, because that's what processes actually execute. And that kind of structure is lost. But a lot of the structure really gets transferred in an easy way to the assembly code. And so we try to make this way the instruction encoding hides the structure of the code and what are individual commands and stuff like that. We try to reverse that so we can get better compression. There'll be some assembly code in this section, Intel assembly code. If you can't read that, just ignore it. It's not that important to understand it. It's all color-coded, so you can see what's going on and see what I'm talking about. This code example, which is just a dump from one of the Werkzeug routines, just a disassembly listing, with the actual code bytes, which is what the processor actually gets to see and gets to execute, highlighted. Now this is all in different colors, and I colored this differently because those byte values encode different parts of the instruction. Some of that is addressing modes and stuff like that. Some of that is operands, and as you see, it's basically a random mix of different data types. It's first a few bytes of opcodes, then it's an address, then another opcode, then it's some relative offset, and this kind of data always has a very different distribution, a very different meaning, and it's all munched together because that's all the information the processor needs to execute, and it all needs it for this one instruction. So it's all in there in the sequence in which the processor needs it. This is obviously a good idea when you're trying to build a processor, but not a good idea if you're trying to compress it, because you want to separate data that has a different meaning, and put everything with a similar meaning together, so you can exploit the structure better. And what I color-coded here is different types of the opcode encoding for Intel instruction. Like here, you have instructions with some parameters, some addressing modes, and this gets translated into that string here. And the red one is an offset and stuff like that. So you can see here what gets mapped to where, and you really see it's kind of weird. It's very mixed. And it's not that it's systematic. It doesn't look very systematic. The reason for that is that the original instruction set was for a 16-bit processor, had far less instructions, and was based on completely different concepts. They always added and extended that architecture, and basically added a lot of hacks too, and it's all very patched up by now. Because, yeah, it's a 20-year-old architecture, at least the original idea, and they always did some changes and some modifications, and by now it's basically a mess. You always have those different types of data in one big data stream, which are, for example, actual instruction opcodes, like the black ones here, or address displacements, like here, those red ones, or addresses themselves in the code and in the data and stuff like that. It's all mumbled together. And those values have completely different characteristics and completely different distributions. So what you want is to separate those again, so you can exploit the individual structure in each of those data types. So how can we improve this? How can we separate this? The idea is the same one as before, actually. We try to group data that sticks together, that belongs together. And we don't want to have to store some elaborate metadata that tells us how to decode this again and put this back into normal x86 code. There are several reasons for this. One main reason is that you want this to be reversible, because it can always happen that, someone has a jump table or whatever in your code section where it doesn't really belong, but it's just random data in your code section, and you want to be at least able to still decode this correctly anyway. So you need some mechanisms to decode that, but you want it without additional overhead. And can we get away without storing any metadata that stores us how to decode this in an efficient way? Well, I wouldn't be mentioning this if you couldn't, but you try to stay with the basic opcode encoding, because the processor can decode it, so we can too, and it also means that we don't have to do any additional processing after the reordering stage. We don't have to translate that back into executable code again. After we've undone the reordering, you can just jump into it and execute it. But we try to split it into several streams. To do that, to find out which one of those bytes, which is everything the processor actually sees, this byte stream, is an instruction, which one is an address, which one is a displacement. You need a disassembler. It doesn't need to be a perfect disassembler. It doesn't need to be able to give you instruction names of the actual encodings. And some things like prefix bytes, you can just treat those as if they were individual instructions. But it needs to be able to determine what type of data is what. What is an opcode? What is instruction data? What is address offsets and so on. And you need to be able to determine instruction sizes so they don't get out of sync. This sounds like a total overkill, because writing a disassembler just to be able to pack some code, this really sounds like overkill. But you don't need much information. You just need a bit of flags, actually. And what I do in Crunchy is a very simple table-driven disassembler that fits into about 200 bytes, plus another 256 bytes of tables that are everything I need to disassemble x86 code approximately. This is not perfect, but it's reversible, and that's enough if you're doing compression. So, another interesting point is call instructions when you're calling subroutines. This is important because when you have a high-level language code, you call a lot of functions. Most of your code lines are probably calling functions in one way or the other. So this happens a lot, and those call opcodes are quite big. This is 1 byte for the actual operation that tells the processor now the call coming up, and there's 4 bytes, which is a relative offset to where should I jump from here, how far to get where I want to be. This is relative, so it's no problem to move programs in memory. That was the original idea. If you have to load a program at a different address, you can do so without having to patch every single call, because the relative offsets don't change if you just move it. But it hurts compression, because usually some functions get called very often, others just get called a few times. But those that get called several times, you would expect to get some gains in that, because it's this call-up code and the same address, and you have that several times, so you would expect some compression. But with a relative offset, the offset you see for this call instruction is different every time a function is called, because it changes every time. So relative offsets are different each time. So you transform that back to absolute offsets by just adding the position of the opcode back where it is in the source file. This improves This improves compression by a few percent. I didn't have the time to prepare actual numbers because it's actually relatively hard for me to test, because I only have the sophisticated code filtering software and I don't have old versions lying around anymore. And would have been a real work to just turn that back into the basic one, so I can tell you the exact ratio, but it was a few percent, 3% or so improvement. And this kind of technique is used by UPX and other similar exit packers. But we can also take that one step further, because a lot of those functions get called several times. You don't, even if the offset is the same every time, you don't want to code it every time by itself. What you do, you keep a list of locations that got called in the recent past. Doesn't even have to be unique. You can have the same entry into multiple points in this list, doesn't matter. This makes list management a bit easier. And if this offset is in the list, you just code the index in this list instead of the actual offset, which is a 1 byte or even smaller index instead of a whole 32-bit address. And doing this on this already absolute transform gives you another 2% code size improvement after packing. And still, we're not through, because you can, when you have that kind of logic, where you actually try to exploit the structure of how call instructions look, you can go even further and look at how functions look, because those are most likely call targets. Functions are what you're trying to call. And if you're using the Visual C++ compiler, like we do, for example, the spaces between functions get padded with a few breakpoint instructions, which is just there so you notice an error if you accidentally, by some way or other, jump somewhere you shouldn't between functions. The idea is just that you catch this kind of bug. But you can, this kind of opcode wouldn't be executed in normal code flow. But you can use that to determine where functions start, because each time you have this padding with breakpoint opcodes, you know, okay, the next non-padding thing we're going to see is probably the start address of a function. So when we see some padding sequence, we just add the end of this padding as a potential call address and hope that it is actually a call address. In the worst case, it's just happens to be that you actually use this breakpoint opcode somewhere in your program, and that entry will not be used. So you lose one table entry, and it's not really a big deal. But that way, we can usually predict call targets even before they first get called, so we can have a good guess about what's going to be a function and what's not, even though it's never been called. Actual hit rates for this are very high, and most intros are packed with Crunchy have done some checks. You get a 92% hit rate on this. So 92% of all calls are encoded with a complete offset, but only with this index number, because either we found it first, or on the second call it gets coded with that index. So this really helps a lot, and it gives you another 1.5% improvement on top of everything else we already had. By this point, we've saved, for example, on Candytron, by this point you've saved about 3.5 kilobytes just by reordering call addresses and storing them in a different way, which is not that much code to undo. This is just a small table and some assembly code to undo it. So it's very simple, and it gives you a great gain. Okay, so that's the end of that example, and we're close to the end of the talk. I'm just going to sum up things for the end. And I gave you lots of rough introductions as to how different compression algorithms work, what they are trying to do, and it's not that important that you understand all the details. If you look at most compression papers, they are terribly hung up in the details, but they don't actually tell you what it is trying to do. For example, this code reordering thing, that was not my idea. I got that from a paper that tried to do this in a context modeling framework. And all it's doing to do, really, is trying to split those instruction streams. But the way they described it was a lot of stochastic models and very complicated terminology, so it's hard to read, but the idea is really quite simple. It's the same all over the literature, so you have to be careful when reading that kind of stuff. It's usually fancier than it has to be. And yeah, just don't get too much into this when you just want to improve your compression. The details are not that important, actually. It's important what kind of data your algorithm can pack and what kind of structure you can exploit and what works well and what doesn't. And transforms are the key to that. This is what makes a huge difference. This is what makes the difference between an intro that is 64 kilobytes and an intro that is 80 kilobytes. You don't have to overdo it. Simple transforms are usually best. And it's very easy to do usually. Reordering in this LZ and context-based schemes is very powerful and again usually simple to do. And the key to that is grouping data by structure and optionally doing some very simple scheme like delta coding afterwards. And for all you do, you really have to measure if it gives you a gain or if it's just a waste of code size. You want to be sure that everything you do is actually worth it. And finally, these examples of some of the things I did. I didn't want to overload this talk with too much information. I hope that the ideas came through and the general design strategy, the kind of stuff that you have to try to understand the type of data you're doing and try to make the packer understand the type of data you're trying to compress, because that's what actually gives you compression gains. Still, it's heavily dependent on the type of data, how much you can gain. Your mileage may vary on that. Okay, so final questions and answer section. Any questions? Come on. I don't believe you. Yeah.
But explicit and implicit dictionaries, the compressors, you said there's advantages to code the references so that they are as short as possible for those for those entries which come often, and it's possible with streams with explicit dictionary. But with implicit dictionary, am I understanding this correct? That arithmetic coding or similar systems that are afterwards do mostly the same, with an added benefit that it also works for the data.
No, the actual benefit in doing implicit versus explicit coding and that kind of framework is that in explicit coding, you just get a sequence of coded strings. You fill up your dictionary initially with single characters and add longer strings as you go. So you always have codes in this dictionary and you never leave it. The advantage of implicit coding is that for every character, you can actually decide whether it's worthwhile to code a match reference or just use the arithmetic or Huffman code or whatever you're doing. That's what gives you the difference, and that's what makes it easier to integrate. Because when you have Huffman coding, say, on the explicit dictionary, you have to code all the dictionary entries. And this can be a large number, and it can be hard to get statistics and that kind of stuff. The advantage of implicit coding is that you can really keep the dictionary scheme and whatever else you're doing separate. That's what gives you the advantage in coding, because you can just decide on a case-by-case basis what is the better idea to code something. Okay? Any other questions? Yeah?
Did you also investigate Borrows-Wheeler transformation or something like that? Or do you know of any packer that uses it?
Yeah.
Explicit packer, of course.
Yeah. BZIP uses it, and the problem is, in an intro context, it's not really useful. A Borrows-Wheeler transform is a very interesting algorithm, a very interesting transform algorithm, actually, another actual coding algorithm. But the problem is that it really just works well for large amounts of data. Say, you need a few hundred kilobytes at least. I've done a lot of experiments with that kind of algorithm, but I've never managed to get interesting compression rates, like a lot better than LZ schemes, in an intro context. So, yeah, just not used it so far. I've done some experiments, but it's usually not worth it for intros. Yeah?
Have you ever thought of writing your own kind of virtual machine with your own opcode?
We've thought about that. We actually started writing a forth-based intro system with some kind of forth, if you don't know, it's a stack-based language. But the problem is that writing intros in this kind of language is really a pain in the ass. And you don't want to do this. So we tried this for a few months, but it really wasn't worth it. It wasn't worth the work. It wasn't worth the gray hairs. So we just skipped it and said, okay, we still use C++ and try to make C++ compiled code compress as good as we can. But I know some people who've tried successfully to use it for case. So it can actually work, but it's really, really, it's basically annoying to code that way, at least for larger projects. Okay. No questions anymore? Yeah?
Just one quick question about interrupt-free stuff.
Yeah.
You said, I have 3 slides before.
Yeah.
That's just something that you use to find the begins of functions. That
Yeah.
Okay, so it's just something.
This is
you
just.
don't use it. It's not really anything used for compression. It's just.
It's just something. That's an interesting property.
Structure.
Yeah, that's an interesting property of Visual C++ compiled code that I can easily use to deduce beginnings of functions. Because you usually don't have breakpoint opcode, so that the whole code I can just treat as if it was a beginning function marker. So it was kind of neat, but it's not necessary now. Yeah.
Why didn't you use the map files coming from the compiler?
I use them too. But the problem is, the interesting thing about this code stream thing, you need to undo all the transform stuff in the depacker. Everything that's in the instruction stream, like in 3 opcodes, I get anyway. I don't need to code them explicitly. When I do a map file, I need to store that map file information separately, so it gets bigger. Okay? Yeah. And yeah, Ronnie was just winking to me I should stop. If you have any further questions, we can just do it here, but another seminar has to start soon, so that's the end. Thank you for visiting.